Hi, everybody. This is Dr. Nigro with the Chem Calculation Screencast. This screencast is going to look at how you calculate the average atomic mass of an element. All right, so what does that mean, average atomic mass? All right, well, if you look, the periodic table lists a mass for each element. It's usually right underneath the element. All right, and this mass is not a whole number, it's a decimal number. All right, and that's because this is the average atomic mass of the element. All right, and that means it's taking into account all of the isotopes of that particular element, and it's averaging the masses of those isotopes to get this average atomic mass. All right, so it takes the isotope their mass and abundance into account in this calculation. All right, this number should not be a whole number. Just by definition, the isotopes have different masses and you're going to have different abundance values, and the chances of you getting a whole number for the average atomic mass is going to be next to zero. So you should never see a whole number. If you're given a whole number and it's referring to the mass, then what you have there is the mass number. All right, and the mass number and the average atomic mass are two very different concepts. The mass number is for a single isotope, and that tells you the number of protons plus the number of neutrons, and it treats these entities as having an atomic mass unit of 1. So this is going to be a nice whole number, but that is not what is on the periodic table. All right, instead, that average atomic mass is a weighted, oops, spelled average wrong, sorry. It's a weighted average calculation. All right, so what does that mean, a weighted average? Well, it means that because these isotopes aren't all present in the same abundance, then those isotopes that have higher abundance values have a greater effect on what the average atomic mass is than those that have a lower abundance value. I always equate it to the US House of Representatives, the states that have large populations like California, Texas, New York. They have more representatives in that body, that House of Representatives. States that have small populations, like a Rhode Island or, I don't know, a South or North Dakota, right? They're going to have less representatives because they have lower abundance values, if you want to think of it that way. All right, so the formula for this calculation, all right, let's say, I'm just going to set it up. So this is the average atomic mass. I'm just going to make up something of element, we'll just call it element Z. All right, so element Z has 2 isotopes, and we'll call them A and B. All right, so the average atomic mass of Z is going to be equal to, all right, the percent abundance of A divided by 100 times the mass of isotope A. And then we add to that the percent abundance of B, and we divide that by 100 to get the percentage out, times the mass of B. Now, these two abundance values should equal 100%. So if you're given one abundance but not the other, and you only have 2 isotopes, then the difference has to be the abundance of the other isotope. So keep that in mind. Okay. Now, I've shown you this example has just 2 isotopes. You can have more than 2 isotopes. If you do, you just add another percent abundance of C divided by 100 times the mass of C. And if you have a fourth one, the percent abundance of D. And then you do the multiplication of percentage times the mass and then add them all up. And that's going to give you the weighted average or the average atomic mass of that particular element. All right, so we're going to try 2 problems. All right, the first one, calculate the average atomic mass of sulfur if 95% of those sulfur atoms have a mass of 31.972 AMUs, 0.76% have a mass of 32.971 AMUs, and 4.22 have a mass of 33.967. All right, so what we've got here are 3 isotopes. So I like to organize my information. So isotopes of sulfur. And then over to the side, I'm going to list them. I'm going to list the mass, and then I'm going to list their percent abundance. All right, so first we start with our first one, has a mass of 31.972 AMUs, and the percent abundance is 95.00%. All right, so there's one isotope. The second isotope has a mass of 32.971 and a percentage of 0.76%, so not very much. And then my last one is a mass of 33.967, and we have a percentage abundance of 4.22. All right, so you can see we have our masses and our percent abundances. All right, now we know all the information here, and we're asked to find what is the average atomic mass. All right, so the atomic mass of sulfur. You know what? These tend to take up a lot of room, so I'm going to slide that guy over. Equals, all right, now I'm not going to rewrite the formula. You should, just for practice, but because of room, I'm just going to go ahead and start filling things in. So for isotope 1, all right, I have 95% divided by 100, and I'm going to multiply that by the mass of 31.972 AMU, plus isotope 2, 0.76% divided by 100, and its mass is 32.971, so you can see what I'm talking about running our room here. All right, so I'm going to put this third one just underneath, and we'll have 4.22% divided by 100, and the mass of the third isotope is 33.967 AMU. Now, a lot of times we like to ask questions about predicting what that average atomic mass should be based on the abundance values. And in this case, it's pretty clear that one isotope has the majority or the highest abundance. So if you picked up 100 atoms of sulfur, 95 of them should weigh around 31.972 AMUs. So that means the average atomic mass should be close to 32 AMUs. So when we're done with our calculation, we'll see if that's the case. If it's not, then we've done something wrong and we need to go back and check our math. All right, so atomic mass of sulfur. All right, so I do my multiplications and I get 30.373 for my first piece, 0.25058 for my second piece, and then 1.4334 for my third piece. If I add those all up, 32.057 AMUs. And in fact, our prediction was correct. All right, the average atomic mass of sulfur is very close to that one isotope that has 95% abundance. If you look on the periodic table, your answer should be very close to what the periodic table tells you. It may not be perfect, all right, because when we work these problems, maybe we're leaving out some of isotopes that have, 0.05% abundance. So there could be some other ones that are adding a little bit more mass in there, all right? But for our purposes, we just want to be close. If you'd done this math and gotten an answer that was like 34 AMUs, then you know something is wrong. You need to go back and check your work, okay? So this is a problem where you're given the mass and the percentages and asked to find that average atomic mass. All right, let's look at this second problem because this one's a little bit different. All right, here we're going to be dealing with chlorine, which has two isotopes. The isotopes have a mass of 34.969 AMUs and 36.966 AMUs. So this is going to be chlorine 35, and this is going to be chlorine 37 in terms of the isotope labels. All right, if the average atomic mass of chlorine is 35.453, what are the abundance values of the two isotopes? All right, so again, I like to put together a table. So I've got isotopes of chlorine. All right, I'm going to have a column for my mass and a column for my abundance. I'll start with my first isotope, which has a mass of 34.969 AMUs, and the abundance is unknown. And for my second one, I have 36.966 AMUs, and again, that abundance is unknown. And those all total to give me an average atomic mass of 35.453 AMUs, and that would be 100%, because that's going to be the sum of those percentage values. Okay, so what do I know? Well, I know that my abundance values for my two isotopes have to add together to 100%. So I'm just going to call the abundance of chlorine 35X and the abundance of chlorine 37Y. And if those two have to equal 100, then I should be able to solve for one versus the other. So let's say that Y is going to be equal to 100% minus X. All right. And now I can go into my formula, I can plug in that 100 minus X for Y, and then I'll have one unknown instead of two. All right, so what does that look like? All right, so we start with the average atomic mass of chlorine, which is given as 35.453 AMUs. All right, then we have our unknown abundance X over 100, and that's going to be times the mass of 34.969 AMUs. All right, and then for our other isotope, instead of putting in Y, we're going to put in 100 minus X over 100, and then we'll multiply that by that mass, 36.966 AMUs. All right, so you can see based on my formula, I have one unknown. All right, now to make things a little easier on myself, I'm going to actually take this 100 that is in the denominator of both of these, and I'm going to multiply it to both sides. All right, so that's going to change my mass to 3545.3 AMUs. That just makes things a little easier to deal with in terms of the algebra. Now, you do not have to do that. You can leave it and work your way through in a different order. That is up to you. All right, so this is what we're left with once we multiply both sides by 100. All right, now I'm going to start distributing. All right, I have to distribute this. All right, so I'm going to have 3545.3. All right, this is going to remain as X times 34969. All right, and then over here, I'm going to have 100 times the 36.966. So that's 3696.6. And then minus X times 36.9. Sorry, I ran out of room. Okay. All right, and now I need to start isolating X. So I'm going to take this piece and subtract it to both sides, and then I'm going to add together these two pieces. All right, so when I move the 3696.6 to the other side, I get negative 151.3 AMU. All right, and when I add 34.696 and negative 36.966, I get negative 1.997 times X. All right, actually this should be AMUs, sorry. All right, now I need to divide both sides by negative 1.997, and I find that X is equal to 75.76%. All right, and we said before that X is the abundance of chlorine 35. All right, and Y is equal to 100 minus 75.76. So that equals 24.24%. And that is the abundance of chlorine 37. All right, so you can see that we can also determine the abundance values for two isotopes. If we have more than two, then we need to know what the value is for at least one of them. And if that's the case, then instead of 100%, we would take what percentage is left after we remove that one abundance value we know and then set our formulas up. All right, but you can see it's a good problem. It's a good use of our algebra skills and our ability to problem solve. All right. So again, if you're trying to determine the average atomic mass of an element, you will need to know the isotopes, each isotope's abundance and mass, and then you can use the weighted average calculation to determine what that average atomic mass should be.